Welcome.
All right. Hi, everybody. So I will tell you about new algorithms based on Riemannian optimization. And if you're not familiar with Riemannian optimization, then that's kind of the main goal for me to speak about it and introduce it in detail. So that is what we are going for. I recommend that you try the QR code or try slides.com/my name Marek Gluza, because then you can click on all the links and then you have the interactive deck directly available. All right, so the story today will be actually personal. So I started working on those quantum algorithms 4 years ago. This is where I grew up. And then during COVID, I came to Singapore. That was 4 years ago. And about half a year later, I've put on the archive a proposal for double bracket quantum algorithms. That's what I want to talk about today. And that's why it's a personal story, because I have been working on it ever since. So that's the first paper. And then once I started working on this, I've been kind of on an intellectual journey, working with many people, and it has been quite a fun experience. So one thing that I want to say is that the field is very inviting. So at that moment when I came to Singapore, I have been working on other things in the quantum field, but never precisely on quantum algorithms. By now we have 9 papers on the archive, one or two experimental explorations, and more things in the pipeline. And so that goes to show how fun the experience can be. And another thing that I learned is that once we started thinking about what is going on in terms of those quantum computations, we started working on it as a research program. And that's also a little bit of a different experience that I had, because before that, I was working as we tend to do, one paper to another, and then we try to do our best. And here it's actually a cohesive research line that we have worked on. And the exciting bit for me was that I could exchange ideas with many people. 25 people contributed to this effort over the last 4 years. So that's for me personally a very gratifying aspect of it. And why it was possible to have this research program is because of the mathematical observations that were guiding us. And I will tell you how precisely those mathematical observations are all about Riemannian geometry. And that's kind of the joy that I'm getting these days out of thinking about those ideas. Okay, so that's the kind of context of where I'm coming from with this. So today I will tell you about double bracket quantum algorithms. And then the part one, I will allow myself to put it a little bit into context of how I'm trying to think about quantum computation. Then I will tell you about geometry, and the geometry will have a very fundamental role to play in everything that we want to discuss. And later I will talk about how to use this for designing quantum algorithms. But before we go to the important things, I actually want to exercise a habit and say, let's not do anything and think first what we actually want to do. And I think that's actually an important theme in the field of quantum computation, maybe one of the most impactful areas that we can be working on, to actually think what do we want to be doing with the quantum computer. As I will describe in a moment, the machines become much more realistic, that we will have them in hand. Okay, and then in the end, we will come to the actual double bracket quantum algorithm. So I will show the roadmap again. And next, let me just talk a little bit about quantum computation. So to me, a quantum computer is a device that inside of it will have a very special quantum system. It could be an ionized atom. It could be a loop of a superconductor. What it means is that we can actually make it. So in Singapore at CQT, this is actually the in-house development of some prototypes of a superconducting quantum computer. But also in labs around the world, we actually see those devices. And I think this is actually important for us to remember, that this is actually quite a hands-on experience that we can have with quantum computation. Another aspect of this is that we actually have the entrepreneurial researchers who started companies, and then you can see in the stock markets that they are going through the roof. I'm showing this just as a curiosity, and I'm not qualified to give you any financial advice, but sometimes body language says more than words, and I usually leave it at that. But this is just maybe as a conversation starter. Afterwards, offline, I'm happy to discuss more. All right, so we are switching to the background of trying to do quantum computation. And I want to list a few aspects of, I think, what every quantum computer will have. And then we will see how geometry actually can link with that. So first of all, the quantum system that we want to consider for quantum computation will not be any quantum system. It should be a quantum system which we can model by a finite dimensional vector space. And I'm stressing this because thinking of vector spaces is actually something fundamental to anybody who is working in STEM fields, right? So engineers will know about linear algebra, but also mathematicians and physicists. So this is actually our meeting point where we can talk everybody together in the same language. Specifically, we will be usually talking about the generalization of bits, which means that our vector space will actually have a product structure where we have complex planes tensor to the number of qubits that we have, so the dimension will grow exponentially. And then once we have those vector spaces, we want the whole system to be in some way modular. So if I start adding something to my quantum computer, I want this dimension to grow, which usually means we take more qubits. And once we can do those things nicely, we want to operate on the qubits. So now the quantum computer is a quantum system, but then it needs to become more computational. So to make it programmable, we need to find ways of changing the state, which will be vectors in this linear vector space. And the operations that we will do must be reproducible and reversible, okay? And in plain language, what we will do is almost every qubit that I have seen will be controlled by electromagnetic fields. We can think maybe, is this needed? Is this something fundamental? But then also to make it reproducible, we will use maybe some high-end electronics and things like that, okay? So this is something where the engineers have been very helpful to physicists. And in the last decades, we have made quite a lot of progress on making this always closer to the idealist case. And once we are comfortable with this, we can talk about a universal quantum computer, which will be using those modular operations to grow the size of the computation. And then we will be operating on it in this special programmable way, such that we can eventually reach any vector in that vector space. Okay, I'm trying to talk very mathematically, exclusively about linear spaces, because that's effectively what we want to do by doing the physical thing and then have this model inside. But in the end, this kind of universality is coming from papers from the 90s, and to me, the Nielsen Schwann textbook is still equally valid. If we know it deeply, then usually this is a great start to go to. So that's an overview of how I would look at quantum computation. Just one comment to say that I think it's an interesting question to ask, whether physics will continue influencing the field for the time ahead, because so far, for good or for worse, quantum computing has been influenced by physics. So for example, the Nobel Prize here is actually about those loops of superconductors here, a fundamental discovery in physics, which is actually not so much about quantum computation, because we haven't used a quantum computer for some extremely useful goal yet, right? So if we manage to do quantum computation very well, maybe those professors here will get another Nobel Prize. So far, it's a very, very nice prize exclusively in physics for fundamental physics discoveries, okay? So we need to think, as physicists, maybe we can do actually more, and will this become a very nice interdisciplinary field? Okay, so that's the overview that we have here. Then, to put it in words, a quantum computer will be an experimental setup A, which includes inside of it a system B, and that setup A allows us to manipulate the quantum state of B. Mathematically, this will be modeled by multiplying unitary matrices to vectors from a finite dimensional vector space. Okay, very simple. I tried to make it as simple as possible. I'm very happy to debate this definition as well. But so far, this is how I would look at the quantum computer. So what we have is a little bit like a nice basket. Inside of it, we have valuable fruits, and then we have a naughty cat that wants maybe to disrupt the contents of the basket. In quantum computation, we have something similar. We will have the whole quantum computer in the lab. That's the one actually at NTU in Singapore. And then inside of it, we will have the qubits, and we will need to make sure that the noise of the classical environment doesn't destroy everything that we want to do. And just to lighten the atmosphere, when we see the press releases in news about quantum computation, we see pictures like this. But this is a little bit like showing the casing of a PC, because the qubits are actually inside very, very small. But it's actually very important, and I think it's worth stressing it, because we need to counter the noise that we have. So actually a lot of effort went into that. And I think actually rightfully we are showing the casing of the quantum computer, because that has been the difficulty to realize it. Anyway, so good. Okay, next, for the remainder of the talk, I will be talking about quantum algorithms, how to pattern those unitary matrices to do something useful with the quantum computer. Okay, and we will take this as an outset to build some geometric way of thinking about it. Okay, before we go ahead, still, I think it's also something to think about, that those are just the facts that we have started this here as academics. That's let's say in the 90s, in the 80s, people were thinking about it. But by now, a lot of our research is driven by this, by companies trying different types of qubits and then trying to devise prototypes that would perform those operations that we want to do. And for good or for worse, this is the landscape of quantum computation. So I'm listing this here. If you open my slides, you can click through the list. And I think this is something that we need to understand. It's a new type of technology that is actually very closely linked with companies, and that will be influencing how we will be working on quantum computation. So yeah, it's good to keep an eye on this as well. Good. So what do we want to do with the quantum computer? A quantum computer should be useful for us. And there are three challenges that we have to a quantum computer that we need to keep in mind. So quantum computing cannot be useful if the problem that we are trying to solve can be solved very quickly on this computer, right? If I can run my problem on this computer, I don't need to create this new technology. But also, what could happen is that we have this very sophisticated machine that is solving tasks that are not important to anybody outside of the lab. So then that would also not be very useful. And another thing that we need to keep in mind is that as we are trying to find the problems for quantum computation, there will be some problems that will be too hard for a quantum computer as well. I think sometimes we forget it when we talk about quantum computers, that they will be more powerful than classical ones. There will be also problems that we cannot solve. So just to give you some examples, recently there was a discussion that maybe some banking institution could do trade bonding faster by using a quantum computer, but then people realized, well, I could simulate it on such a computer as well, or on my laptop. So then it's not something that requires developing this technology, right? So this application, I think it's good that we are searching for them, but it's not yet the problem that we need to be looking for. Then another thing is around COVID, we had the beautiful realization by a company, Google, of a purely academic problem. They were sampling strings of zeros and ones. I can give them to you as well. Okay, 0, 1, 1 was 0. And then they actually show mathematically that sampling from such a distribution, a laptop or this kind of device will never be able to do. Even a supercomputing center will also not be able to compute such random samples with that distribution. But so far as we know, using this distribution is not useful for any Monte Carlo or any physical application. Okay, so even though we were able to realize it, we cannot use it. And then just to list some problems that we will probably never be able to solve very quickly with quantum computers. For example, mixed integer programming for optimization in industry or shortest vector problem. Okay, so those are a few constraints that we have. And then it's a little bit like this Indiana Jones movie, where classical computation is very powerful. Then there's a difficult, important, and doable problem that we want to find. And we want to kind of manage to use it and kind of escape with this. So if you think who is Indiana Jones here, it's, let's say, millennials who are trying to deliver on the promise that is actually possible to find this beautiful problem that will be actually showcasing that actually we can do better than those kind of devices. Okay, so that's kind of the landscape that we have. Okay, good. Then just to introduce a bit of notation coming from physics, if we have one qubit, then we have a linear vector space that is two-dimensional, which means it's spanned by two vectors that are orthogonal. Then we denote the vectors by so-called cats. Those values here will be our computational states. And then we can think about the general states of manipulating a qubit, which will be any vector in our two-dimensional vector space that we will denote in that basis of 0 and 1. And here we have a fundamental object in linear algebra, a linear combination. And actually, I'm showing here my chessboard. dual to this is a physical effect, which is quantum superposition. So that's the first moment where we encounter a duality between fundamental objects in mathematics and in physics, and they come together nicely in quantum computation. And then in terms of the notation, well, that's the useful stuff that we usually do. The vectors will be in the Greek notation. And then if we have a dual vector, we can use the Hermitian conjugation here. Then we call it bra. Then probabilities will be scalar products in linear algebra. We denote them as projections and just gluing together, forming a bracket. And yeah, the notation that I will be using throughout is if I have a matrix acting on a vector, then in bracket notation, it will be some matrix H acting on the vector, so the cap psi. And the cost function that we will be looking at will be similar to this square optimization. So a scalar product of VAV as a scalar product will be psi as a bra, H, and then psi. This will give us real numbers. Okay, so that's something I can show again, but that's basically the linear algebra that we will need. Okay. Good. So what will a quantum computer do? A quantum computer will be scaling in the modular direction, having always more qubits. Then the dimensionality of the states will be growing as the basis is growing. And then eventually the quantum computer will be realizing those states for us, which means it will be able to manipulate the coefficients of the linear combination through the physical effects that we will be using. Okay? So a quantum computer will be a machine for realizing such linear combinations. And when we talk about quantum algorithms, we actually move to a more systematic way of thinking of those vectors. We will be talking about the operations, which will be unitary matrices from a reference state. Then such unitary matrices we will be decomposing into the operations, and that will be our quantum algorithms. Okay. Maybe we can switch on the aircon, or it's becoming a bit hot. Good. So the next thing I will talk about is those operations that we want to study. I'm going to be very basic here, but I think it's very fundamental, and then we will see that actually the geometry of those operations is very useful for us. So if I have a d-dimensional vector space in my quantum computer, then I will be operating on it by multiplying to the vectors matrices, which will be square matrices, such that the inverse can be computed by Hermitian conjugation. So I just transpose the matrix and then perform complex conjugation. Okay? So this is Hermitian conjugation. If a square matrix satisfies this, it's a unitary matrix. But there's something also more important about unitary matrices, namely that they form a group. Okay? So if I take two matrices satisfying this condition, I can multiply them together and ask what happens if I take this Hermitian conjugation, will this be again the inverse? So using the rules from linear algebra, we can see we need to swap the order here. We have m prime n prime dagger here, which is the inverse. And so we get the identity here. And the next one is again unitary, so it's again an identity. So that's a group law for this set of matrices. So we are dealing with a mathematical group, which has a multiplicative group law. And yeah, and that's very important for us. Why this is important is that each of those unitary matrices is an operation that we could try to put on a quantum computer that transforms one state of the quantum computer to another. If we do two such operations, then we can ask what is the joint operation, and that's given by the multiplication. So if I have them individually, then the joint operation is this group law that we have. So that's the second duality between fundamental things in mathematics, the group law of unitary matrices and the compositional law of how we evolve systems by switching the order of just composing operations. Okay, good. Happens. This is nice. All right. So we were talking about putting those operations together. And if I put operations together, I get a new operation. So now the question is, what happens if I compose sufficiently many operations that are taken from a very fixed state set? I will take some operations from inside of this continuous set. It's a very large set of operations. And I fix a few unitary matrices. And we come to the notion of universality, namely there should exist such a set of k matrices, so let's say 12 or just a fixed number, such that if you give me a unitary matrix from this set, any matrix like this, then there should be a sequence of how to compose those operations such that I approximate the matrix M. Okay? If that is possible, then this gate set is universal for the set of full operations. Okay? So that's the notion of universality, and showing that this is possible with very few matrices to get the approximation of the entire set of unitary matrices, that's relatively easy. What is a little bit harder, and it's actually very, very hard, is to find those sequences. They exist, but what they are is another question. It's a question of optimization, and that is very difficult in terms of computation. So the task of finding those sequences we will refer to as unitary synthesis. We are synthesizing a sequence that is giving us this approximation. Okay? So I will come back to this task more because that's what we want to do in quantum algorithms. All right. Good. So that was the discussion of the setup in quantum computing. It's coming near in terms of the realization of the hardware. And then we will be looking at linear vector spaces and the transformations of the vectors from those finite dimensional vector spaces will be unitary matrices. So let's look at the geometry of those matrices, okay? So if we have more qubits, then we need to think about general notions of geometry. And then the name that we need to think about is the Riemannian geometry, which historically came about as the generalization of the geometry of the sphere. Okay, so I'm showing the watermelon as the sphere. And there are a few generalizations that survive. So if I would have only one qubit, we know the block sphere is a perfect model for all the operations on the qubit that we can do. So that works. But then if we go to higher dimensions, a few parallels remain. For example, the set of quantum operations, which is the unitary group, is compact, which means my friend is able to hold the watermelon in his hand. Usually a watermelon is bigger, right? So I cannot always hold it. So this survives. But some structures get lost. So I'm showing the watermelon here. If you imagine the dark colors here are valleys and those are mountains, it would appear very rugged. And very easily we can have non-convex submanifolds in those high dimensions. And that's something that we just have. Okay, so this is just something we will see. But the most important aspect, how to generalize thinking of the geometry of arbitrary operations on a large quantum computer, is the notion of the tangent space. So imagine my friend takes the watermelon and pops it on the table behind it. Then the table is tangent. So if I want to rotate the watermelon, I can just say in that direction, rotate towards that line. And those are the tangential directions, even though my state space is a complicated curved manifold, I can still always think of a tangential direction to it. And just keeping this tangential notion in mind, we can think of quantum algorithms very nicely, and that's what we want to do next. Okay, so I will need to name some formulas that will be useful. So the unitary group is a Riemannian manifold. What we have is that it is an embedded manifold. So you can visualize it as a sphere, but around it there will be all other arbitrary matrices, which do not need to satisfy this condition. Okay, so this would be a flat space. And our manifold will be the Riemannian manifold that is halved. And the other thing is that we can ask, if I have a point in my manifold, what will be the tangent space? What will be the directions that are tangential to it? And it won't be all matrices. It will be special matrices where the Hermitian conjugation plays a role again. So if I have a tangential direction, it should be an anti-Hermitian matrix. So I take the Hermitian conjugation here. I should flip the matrix with a minus sign here. And we know usually we are constructing unitaries from Hermitian matrices, which are Hamiltonians. So we can just add an I here. That will be also a parametrization of the tangent space. Okay. If I take a non-Hermitian matrix, it will not be tangential. Okay. So that's our restriction. And that's a linear vector space of the directions that we can take. Once we have those directions, we can ask, okay, what happens if I consistently fix that direction and continue going in that direction for some time? Okay. What we will have is that we will implement this through unitary operations where we choose the direction, and then the length of how long we go in that direction will be some number s. So if I have anti-Hermitian, I just exponentiate it like this. Or here I will have an I for the Hermitian matrices. Okay. So the matrix exponentials that we know from regular mathematics that we consider are actually geodesics of the manifold. So they are directions where they are curves where the direction is not changing on any point of the curve. It's always the same matrix that will come from the derivative, and that's why it's a geodesic.
Okay, so you are essentially talking about the space of generators, right? And so
yes.
So this is the space of, yeah.
If we think geometrically, we can think of the generators of the unitaries as being the tangential directions. Okay. Good. So once we are happy with this, the other thing that we can ask is, what about directions that point us towards something useful? So for example, a gradient of a function will be telling us about the minima or extrema. Now, because we have this condition for tangency, we cannot take a regular gradient, which would mean I just take a gradient over the matrix elements of my matrix, because I will be working in the embedding manifold, but I need to be working with my complicated Riemannian manifold. So what we will do is derive a tangential gradient that is fulfilling those conditions and yet is pointing us to the degrees of some function. Okay. So here we will need to work a little bit harder. Okay. But the tangent space will help us to work with that. Before we go to that, we can study one more thing about the geometry of our manifold. So it's just a set of points, our manifold UD. We can see that it is curved. The way we will do that is to say, I will take two geodesic. One geodesic will be going south in the direction A, and the other one will be going west in the direction B. And then I want to form the cycle. I went south, I went west. I now want to undo going south by going north. So the inversion is just by flipping the sign here in the exponent. But the direction is the same. It's just we are going in the opposite direction, but from a different point. So now for the case of a qubit, you see that I'm working here around the North Pole. And if I undo going west by going east, I will spiral away from the point of origin. Okay? Now imagine doing this the same on a flat space. I went south, west, north, and east, I come back. And this is how geometrically, by never leaving the manifold, you can check whether your manifold is curved or not. Okay, that's the work of Gauss and the mathematicians. So now this fourth cycle is pictorially spiraling away. If we want to study it further, what we will do is to say, I am composing some operations on my quantum computer. So we actually explicitly derive the group law. If I compose going south and west together, it is a joint operation. This is a unitary matrix. I multiply more unitary matrices. So those four matrices are unitary. And now we can ask, what is this unitary matrix? We already know it generally will not be the identity. It will be only the identity if they commute. That's the flat case. But if they are not commuting, it's not the identity. Okay? So we want to study what will be this matrix. It's some unitary matrix, but what is this matrix? Okay? Good. So this is different than the flat case, and that's where the Riemannian geometry is coming into play. Okay, before I answer this question, I will study a bridging calculation together with you. We want to study all those unitary matrices to find interesting things we can do on a quantum computer. So I propose this matrix, and first of all, I will show to you that this matrix is unitary. So I will take two Hermitian matrices. I will form the commutator of those matrices and take the matrix exponential. Then I get a matrix, and I want to show that this is unitary. Okay? So what we want to show is this is unitary. And in between, we will show that the commutator is actually anti-Hermitian. Okay? So we just need to compute the Hermitian conjugate from here. Okay, so I will have AB minus BA, take the Hermitian conjugation here. Then I need to flip the order, BA, AB, but they are Hermitian, and you see this is minus the commutator already. Okay? So this is anti-Hermitian. And let's have a look how this plays out. So I have my matrix here, and I want to take the Hermitian conjugation here of the exponential, which means I need to exponentiate the Hermitian conjugation. but this is minus that operation, and that's literally the inversion of this matrix, right? So this is a unitary matrix, okay? And now, okay, it turns out that for this fourth cycle, which we consider geometrically as a thing to study the curvature, it turns out that the commutator here is literally the answer to what we have here to a very good error. So if this fourth cycle is a very small thing, instead of going on a big patch, I'm going on a small patch, then the commutator exponential is the matrix that I'm implementing through those four operations. Okay? So now imagine this is the individual operations that the quantum computer gives you as a basic thing. A new operation that in general will be different, and you get the power to do something new. Okay? So that's called a group commutator, and it has been known before. But the next thing we want to talk about is that actually I'm switching the background because this formula here is the main tools of the quantum algorithms that I want to describe. They are actually extremely useful, and we will see why. The reason is that it will actually tell us something how to implement those special geometrical gradients, okay? The ones that fulfill the tangency. Okay, good. So, okay, we want to get there. But as I said before, we jump to part 4 where we will do quantum algorithms. Let's talk a little bit more about how to use quantum algorithms because, yeah, that's a new type of computation, so why not think about this some more? Okay, so for me, there are 4 stages of creating quantum algorithms. First of all, I'm saying, okay, let's not do anything and let's think about some problems that this old device cannot solve easily. And then once I identify such a problem, I need to start a journey towards the interior of some wild jungle. And the first step I need to do is to formulate the problem that I want to solve that this cannot solve as a linear algebraic problem. So I need to start with a vector, and then I need to say the quantum computer will be rotating that vector into an output vector, and I need to encode that problem, okay? So the output vector needs to be able to give me some answer. And there's many different ways how I can encode a problem into vectors. And so that's a design choice where the efficiency, how I'm encoding the real life problem into linear algebra or some vectors, that will decide strategically how we approach the quantum computation. So first of all, we will decide what is the starting point and what is the end point, how it will be described. I will give some examples later. And then we need to map from this input to output through unitary matrices. Those are 2 different things. This is just setting up the problem specification in language of linear algebra, and this is using unitary matrices to implement it. Once we have the unitary matrices from unitary synthesis, we can decompose them further into smaller little operations that the quantum computer can do. Okay, so it's a cycle of 4 stages to design a quantum algorithm. And then later I want to tell you that the double bracket quantum algorithms that we were developing is a systematic framework for performing this unitary synthesis for quite many choices of how to encode different problems. Okay? So let's think about this design problem a little bit more. Well, we were discussing that several ideas don't fulfill those criteria. And my claim is that material science is actually the right thing to think about. Okay, so why material science? Well, that's a good question. And first of all, whenever somebody says, okay, there's a useful problem for a quantum computer, you should keep in mind that when a lot of people can gain by having something to say, some of us will not resist the temptation to speak without having much to tell. Okay, and that's the hype in quantum computer. Maybe I'm actually lying to you. Maybe material science is waste of your attention. Right? Might sound cool. Maybe I feel better by saying material science, but maybe it's not a good direction. Maybe you should think about some other problems, how to use the quantum computer. And the problem of hype is starting actually with quantum computation, because already one of the first best algorithms that we found was done initially by Shor, who showed that quantum computers can break the cryptography. If we think back, this is the rabbit hole that started the whole adventure of quantum computation. And already 10 years later, so I'm showing the QR code here because there's a brilliant essay by Shor, and he, 10 years after he proposed his algorithm, he beautifully lamented why have not more algorithms been found, okay? Already 10 years later. And his answer was, well, maybe the easy ones that we can do on classical computers. So that's this ball of classical computation that is chasing us, trying to find good problems. Or we have found no good language. So in this jungle of possibilities, we are not able to navigate it well yet. Okay, so that was his answer. To see what else was happening in the meantime, you can visit this webpage here, Quantum Algorithms Soon. And if you look carefully enough, you will see there's hundreds of algorithms, but those algorithms are of the type of applying underlying distinct subroutines that are solving some problems. And the way I think this is true is that classically, any computation that your laptop is running can be theoretically decomposed into a sequence of decision problems to ask yes or no, then go to a different question. And those kind of decompositions we can think of as being the underlying quantum algorithms, and then the applications who are querying those algorithms. So in quantum algorithms, Zoo, you can think of which algorithms are the fundamental ones. In quantum computing, the decision problems will be asking, well, I have some state psi. Can I rotate it in such a way that this expectation value of energy here, psi h psi, can this be a number that is below some threshold? And that's asking for a decision problem. And those kind of algorithms solving those problems are usually the underlying subroutines in many of the algorithms that you will find in the Zoo. Okay? Okay, so that's kind of the landscape we have. And now I said, well, material science we should do. So within this whole scope of trying to look for different problems, I think this is worth hyping, and I am very happy to debate it. So why material science? Well, imagine that you're working on a photovoltaic cell. We want to move to solar power. If we had a powerful machine that from the beginning gives us 1% more efficiently, 1% more efficiency, then imagine you unroll such a device to a large scale, then directly you get 1% more energy out of such devices. So working on material science could have like very big kind of amplified results for whatever we are doing in society. And we actually know what we need to do. So we will need to use the quantum computer, which has nothing to do with photovoltaics, to go into low energy states of the Hamiltonian from material science. But those Hamiltonians actually we can write down very nicely and put onto the quantum computer nicely. And then we need to devise quantum algorithms to do physics and study the physics of the system. Yeah? So basically we will be quantum computing physicists one day if we want to study material science. Okay, so I'm happy to discuss this more also afterwards, but that's just to give one application of what we should do. And so this is just to motivate that we need to optimize among all operations of the quantum computer to get a low energy state. The Riemannian geometry that I want to talk about can lead to quantum algorithms that do this. And what we will need to look at is the energy cost function, this kind of scalar product that we also know from linear algebra. Okay, so that's the plan ahead. And I want to use geometry next to tell you how to find quantum algorithms for those kind of problems. Okay, so that's our Riemannian manifold. We have many different directions that we can take. We have our cost function now. And the update we will be taking will be some element of the tangent space acting on the state. And we hope that the state after this rotation will be lowering the cost function as one step of an iteration. Just as a word of caution, not every direction A will be helpful. So if I have a matrix here, H, it comes with the cost function, I could use it as a direction, but by a simple calculation, we find that such an update would not be changing the cost function.
So Marek,
Yeah.
you are optimizing cost function, like I see.
Yeah.
But suppose you want to solve a problem, then there is still gap of reducing that problem to this problem, right?
Yes, yes.
So that is not always very realistic.
Yes, but I could argue that this problem is universal for quantum computation, at least theoretically, because adiabatic quantum computation is universal, and adiabatic quantum computation, all it ever does is to go to the minimizer of such a cost function. And yes, indeed, if you have some problem out there in the scope of things we could do, to find the encoding is not easy. So that's the design question. How do you put that on a quantum computer? And how do you do it efficiently enough?
I mean, all Hamiltonians might not be realizable.
They might not be what?
Realizable at some interaction between physical systems.
Yes, though what we think is that all Hamiltonians that happen in materials, we can actually quite efficiently simulate. Because the standard model tells us there's only quadratic interactions. There might be effective interactions that are more complicated. But in the end, those are few qubit operations. And then we do, let's say, if the system is evolving, we just need to do the evolution of that Hamiltonian. But as long as the interaction is not involving the scattering of too many atoms, then this looks a little bit like the regular few qubit operations that we can do. And then we can propagate it to a larger circuit. So let's say how to think about it is there are different stages of how quantum computation will develop. Right now, we cannot simulate any material. We can simulate only materials that are very close to the architecture. In the future, we will be able to do longer computations. So we will be able to bear the cost of the overhead. Okay.
So, sorry, I didn't understand. What is the material here?
Material science could be, for example, I have a solid state structure, and I want to, first of all, simulate the physics where the energy is showing some quantum degeneracy in the solid state, some kind of quantum effects. And then once I reach those states,
Dynamics.
no, first of all, I need to reach a state which is a low temperature state of that Hamiltonian, of the interactions of the electrons in the cells of the solid state.
So some dynamics.
No dynamics. First of all, a low temperature state. And once I have this one, I can perturb it and look at the dynamics to see the response function. But if I do it on a...
Prepare that state that you're saying.
Sorry?
You have to prepare this.
Yeah, that's what it is about. That's what it's talking about.
Yeah.
No, so you start from initial state that you cannot claim to be low energy, right?
Yeah, but the point is, how do you then lower the energy? Like, how do you prepare a state that is,
So you start from any state and then lower the energy to dynamics.
and this, for these kinds of things, you just assume that you know the Hamiltonian, more or less.
So that was the first question that, for example, if light and matter are interacting, then you cannot write any Hermitian operator.
So here, when he's talking about, say, particular, say, chemistry or materials, you're kind of assuming that you have a Hamiltonian, which is nice. You can be written as, say, some sort of
field.
yeah, you can write it down as say
But
some
then still I have limited options only. So if I think of as an effective Hamiltonian or say in field theory, then I am considering like a lattice of atoms or something. And then I cannot have arbitrary kind of Hamiltonian.
You cannot have arbitrary. But the expectation is that for materials of interest, so that's an assumption that for materials of most materials of interest, or most molecules of interest, Hamiltonian can be nicely expressed
Right.
in terms of say
In
molecules.
condensed matter, if I read Hubbard model, it's way good enough, like big enough to encompass a lot of things.
Yes. But what is one example of a model that you think you cannot use?
So I'm thinking there are like infinite Hamiltonians and I don't see all Hamiltonians.
You give me one example that you cannot use.
So for example, cubic or say higher power Hamiltonians.
Higher, sorry?
So say x to the 4 or something.
X to the 4. Yeah, you can do that.
So anything which will have many body interaction.
Many body interactions is perfectly fine, as long as it's local. And as long as there's not too many scattering elements. Because if I have a clump of arbitrary many, I might need some effective theory.
Yeah, that is what I mean, probably. So you have say nearest neighbor interaction kind of thing. Those are more physical exchange. But those are more amenable to mathematics, I think.
Sorry, it's not?
Those things are like solved mathematically as far as
Take the Bose-Hubbard model, for instance.
Bohr-Hubbard model is a good example, but we can have very complicated Hamiltonian simulating the electronic structure of a molecule. We might use DFT to come up with the right orbitals, and then in that Fock space that is the effective active space, we might be solving it. So there might be some effective tricks that we do. But I don't know of a single Hamiltonian that a theoretician would write down to model an experiment in real life that you cannot use. And my argument is, well, if, in the worst case, I will start simulating the standard model. But because if I have a big quantum computer, I can do those overcuts in principle, right? And everything that you will meet in nature is coming from standard model, which is not creating too many scattering events. And if I have few scattering events, then the effective model will have to be a sparse model that I can write down with qubits.
But what about the Bohr-Hubbard model? I think that should be difficult.
There's progress from the last year about simulating by a qubit. So theoretically, we can actually bound that a few level system can actually capture a lot of the physics. So for dynamics, there was a lot of progress on deep Robinson bounds for those models. We also have progress. So actually, we are getting more and more information about this. One difficulty is I will make a lattice discretization, and maybe I cannot simulate a continuum system. But that's not a problem of quantum computation. That's a problem whether intrinsically there exist continuous models that I cannot model through a lattice where I'm taking the lattice spacing down to 0.
So also, like if you, so I don't disagree that you can like probably any Hermitian operator and realize it through some complicated system. But some numerics thing, right? That you cannot solve that Hamiltonian to know what is the Riemannian state.
Yes. Okay, that's a good question. In quantum computation, we will have a new notion of what it means to solve a model. So even if I can solve a Gaussian model with some complicated tight binding structure, I will still use numerics. It will be efficient, right? I can solve a graphene flake for 10,000 sites, but I still need to do numerics if, for example, I have some driving or something like this. So even classically, being able to solve a Gaussian model doesn't mean that we can get everything analytically. We still use numerics. Here, what we will do is we will have a black box that will bring us to a very interesting state that is showing relevant quantum physics. And then we will be asking, for example, questions about linear response on those models. And those numbers will be the solution that the quantum computer gives. One example of that. Now, why we call it a solution is that we will not, if I would have this powerful quantum computer, and if I can go to those low temperatures, then I don't care what that model is. So it's a very powerful machine that will be kind of agnostic. And the difference is that we will use quantum mechanics to simulate the quantum mechanical model. And there will be hopefully some advantages that we can get from that. I'm saying hopefully because it's not fully established, but I think we have quite strong theoretical case for that. So that will be a new notion of computation where your solution is any question you ask about the properties of it, if you can bring it down to simulating some dynamics of it and then running some quantum algorithms that we have, that will give solution to questions. So for example, why I say material science, how you would use a quantum computer. So let's say I have a photovoltaic material, and that comes from a complicated doping of a complicated, let's say there will be 5 different atoms with different amounts that I need to put. In principle, you can fabricate them by scanning the concentration and just have 1,000 different materials. But you cannot have 1,000 lab employees that are checking the complicated quantum properties of each photovoltaic cell. So the idea instead is you will ask the quantum computer to check the model for all those concentrations. Then the quantum computer will say, maybe this one, it will be maybe noisy, maybe you cannot do everything, but it will hit you in that direction. You realize it, you see that maybe the conductance is 1% better, and you gain, right? So that will be this interactive way of using the quantum computer. It will be difficult and complicated, and those models that we will need to consider in the beginning, I think for years we will not be able to run it. So there will be some difficulties, but we need to break down the task into simpler steps. Okay? Cool. So I will go back to this task of very simple stuff. I want to start seeing some properties of the material in the state. So I need to lower the energy. And if I lower the energy, I'm also lowering the temperature. That's kind of the assumption. Okay. So we need to find those tangential directions that will update the state to lower the energy. Okay, so we need to find those directions, and that's the roadmap how to do. I'm showing everything because I will break it down step by step, and then we will see how to find it. So we need the Riemannian gradient, and a Riemannian gradient is a unique vector G that is in the tangent space such that the directional derivative will be a projection onto G. Okay, so I need to explain the last line. I will first define the directional derivative. I will take a direction W in the tangent space for the cost function F, and I'm working at the position X. So this is the symbol for the directional derivative. And the definition is something that maybe you remember from calculus, where we are actually computing a derivative quotient. I'm updating my X on the line in the direction of W, and then taking this S to 0. Okay, so if I would project the entire underlying space of X onto this line, that would be a regular derivative. But just I can take it in many different directions. So this is something complicated that we want to avoid. And the gradient is a special vector such that I can compute this limit by just taking a projection of the trial direction, this one here, onto that special vector. Okay, and this G is independent of W. So you change the W to compute this, you can take this new W and project it onto G. Okay, so mathematicians have proven that for Riemannian manifolds, this is all nicely defined, and we can find such vectors. Okay, so we want to compute this vector for the case of optimizing the energy of some Hamiltonian H. Okay, and this G will be some anti-Hermitian matrix that we want to find. So to find it, we already saw that the Hamiltonian cannot be this matrix G. And also, if I have this matrix in the cost function, I can form a matrix out of the vector, which is the equivalent of the position X on the manifold. So I can form the projection onto that vector. It's a Hermitian matrix. So it's like a Hamiltonian, it's in the tangent space. But again, it will not do anything to psi. It's only projecting onto that. So it's not a useful direction yet. So that's one ingredient. There are two more. I need to tell you what's the notion of the projection in the geometry of the unitaries, which will be the Hilbert-Field scalar product, where I'm taking the gradient vector G, the Hermitian conjugate, multiply with W, take the trace. That's the Hilbert-Schmidt scalar product. So that's how we will get the projection. And the nice thing is we are using a trace here. So that there's the property from linear algebra that the trace of matrices is cyclic. So if I have three matrices ABC, I can also shift the C in the ordering and get the same number out of the trace. Those are three ingredients that we want to use. And now we see it again to do the computation. So that's the cost function. That's our update. Now I'm using the definition to compute what's the directional derivative after I update in A. So I will take the limit of S to 0 of this kind of Heisenberg observable here, subtracting the S0 component and then removing everything in higher order. So as we see here, this is just the derivative in S. I can equivalently take this, which is the Heisenberg equation, where I rewrite the expectation value using the trace with the projector. Okay? We can discuss some more how to derive it, but this is just the Heisenberg equation, basically.
Just one point.
Yeah.
Just this may not be obvious to everyone, but because I wanted to put this out. So this effectively you are doing Baker Campbell Hausdorff kind of a, if you do that, right? Then also you will get something like this in first order, and then you get higher order terms.
Yeah.
This is where you can introduce many different orders.
Yes.
Instead of first order, you can go to higher and higher orders, just like they do in Trotter.
Yeah.
And you can get better and better errors.
Yeah, you could do that.
So extending to 0, nothing else will contribute.
No, so of course there will be an sure, but if you calculate
Is there will give you round powers of S and commutators?
so depending on how you break it down, this thing, right? This is an approximate. You can approximate this by using other things, like you can use S by 2
So,
A and you
get
get
computing limit as tending to 0. So it is
Sure.
gradient only. So
Sure.
I mean, I applied directly in the
No, here it's exact, right? Here, because it's x equal to 0, it is exact. But in, okay, continue. I just want to.
Yeah,
But
but
in previous formula, when you wrote for multiplication of 4 matrices, I will apply BCH and get all the powers where you wrote order is cubed.
okay. Let me just continue. We can come back to it. Okay. Once we have this, it starts looking like a projection in space of some matrix times some matrix, but this matrix is not just the direction A that we want. So we need to use this explicitly move something through. And actually the commutator is also adding some cyclicity. So I can move this H outside, or I can move psi inside, and then A will hop outside. And that's what we get. And we can identify the gradient here, okay? So I just wanted to finish the calculation. This, we identified the gradient. So we kind of linearize our manifold and the cost function, finding some kind of linear structure for the derivatives. Derivatives should kind of be linear. And we found the form of the G. And you see that those two ingredients individually that do nothing, if you put them in a commutator, that becomes this powerful vector G, the Riemannian gradient. So that's the third ingredient, the cyclicity we had, and the derivatives and those directions. Okay? So now I have a summary slide. This was by definition. This is our cost function. That's our gradient vector G. This is a direction. So I can go on the geodesic in that direction. What it means is that I will map some state psi into a psi prime, which is given by rotating psi through the exponential where the matrix G is giving me the direction. And what I get is that I know that this is changing the cost function. If I go in this direction, I will increase it. If I go in the opposite with minus G, I will decrease the energy. And that's the steepest direction in some sense. So this new state psi prime out, updated by the gradient, will have a lower energy, but now I can update it. So I can get a double prime by forming the commutator of my psi prime with Hamiltonian. So this operation here is a gradient descent formulated geodesically in terms of the Riemannian manifold. Okay? Good. Now we can speed things up a little bit because we are coming slowly to double bracket quantum algorithms, which is a systematic framework for implementing exponentials of commutators on quantum computers, and that uncovered new analytical formulas how to think of quantum algorithms. So the way we will be implementing it is through this fourth cycle that we saw before. So we started with curvature. It gave us some answer, what is this fourth cycle? And then we can just say the projection psi is A, the Hamiltonian H is B. We need to cycle it through, and it will give us this kind of energy decrease that we want. Okay? Good. So let me just speed things up. If I take a continuous limit of this, normally I'm just trotterizing and updating, I get a linear equation. If you take a limit of what is happening there, we will get a nonlinear differential equation. And just to say why the name of the algorithms is because this is called a double bracket flow. There are two commutators in the differential equation. Here it would be only one. This is linear, this is nonlinear. It has still solutions in terms of unitaries as we saw. We still had unitaries, so that's a good thing. But this nonlinearity is actually a good thing and a bad thing. The bad thing is it's harder to implement. The good thing is that it actually can do computations. So Roger Brockett was the first one who discussed double bracket flows, so equations of this form. In the context of computation, that was in 91, so the year when I was born, he recognized that those equations are dynamical systems that can solve list, diagonalize matrices, and solve linear programming problems. Okay, so this nonlinearity has actually power to do computation for us. As we saw, it can do optimization. Okay, so he actually recognized that you can use it for computation. In classical computing, it didn't turn out so far to be useful, but for quantum computation, it's very useful for us. And just to tell you, 10 years later, he co-authored the paper here on quantum control. And that's the paper that actually we use still to today. If you have an arbitrary 2-qubit computation, how to decompose it into the canonical C0 gates. And they derive the formulas that we can still use to today. Okay, so just to summarize, we came from this Riemannian gradient optimization. If we make it continuous, we arrive at those double bracket flows, and that was my starting point. So double bracket quantum algorithms are actually originally inspired by double bracket flows. And then because we have optimization here, we can perform optimization through hopefully short quantum computations. Okay, so that's the historical note, but now we can come to the main results.
Unitary synthesis is difficult, right? I mean, so I'm not sure what do we know about the complexity of unitary synthesis.
Particular continuous, just this already has
No. Like, if I give you arbitrary unitary discrete systems, and I ask you the number of say universal gates that I will apply, how will you scale the number?
it is not efficient, not polynomial.
And I don't think it's known properly. So,
There are many algorithms actually.
so how does your result contest with that? That in general it is supposed to be a hard problem.
Yeah.
I mean, I don't know the complexity. So, and, I mean, you will not be able to implement like synthesis of any arbitrary unit, right?
So when unitary synthesis is a question of optimization, okay, and there will be different viable solution to the task because it's also an approximation task. So there will be many different composition sequences that will achieve that approximation, and we use equations to find human readable prescriptions how to synthesize the problem, but it might not be optimal in the runtime. So the nice thing is we can write it down, it's available to us, we can run it. If few steps are short enough, we can run it. That's great, we can use it and go ahead.
So you compute the computational complexity as well? What do you?
No, we don't have results on that. This we don't have, yeah. So I will say a little bit more about using double bracket algorithm in this call sequence. So I will talk about a very specific choice of the design problem. So I want to continue lowering the energy, and I will start with some arbitrary state psi that you are happy with, and then I want to map this state psi to the output of imaginary time evolution. Why this is design choice, not unitary synthesis, is because it's a mapping between the state psi into some new vector, which is normalized, but this is not a unitary. So it just gives me two states. If you fix the tau, I have only two taus. Of course, I can continuously move it down. I can get a sequence of states, but I want to take tau just large enough because that will give me a low energy state and then will converge to the ground state. So that's the design choice, how I want to approach the problem. Now I want to find a unitary that maps from psi into this normalized imaginary time evolution. Okay. If I do this, then I solve this here. And that's given here. That was a hint of David Gosses to ask how to do it. So it turns out that the Riemannian gradient unitary, the update that we were looking at, actually in the linear order is approximating imaginary time evolution. And dually, it says that imaginary time evolution, which we know from physics, is actually a Riemannian gradient flow. So it optimizes to the ground state because of those Riemannian optimization procedures. Okay, I will just need to repeat it many times, propagating the small tau. Okay, so this is our bridging formula here that comes from optimization.
How do I get this since you are writing order tau is square there, so it looks like tau is small.
Yes, that's. I will answer this, but I need slides. So we first need to understand how to put this on a quantum computer, and then what we will do is we will form a recursion, because I can propagate it step by step. Okay, so that will be the answer, but I need a little bit of notation to show it, how to do it. Great. So we have this for cycle for the exponential of A and B. So I have A times B, A inverted, B inverted, and then that's an approximation to this one. So instead of the linearization approximation using the gradient, I can do an additional approximation, how to approximate the gradient here. And you see this last one is applied to psi, so it does nothing. So I can just reduce the amount of operations. And that's like a many-body echo. Also something you see in Grover. So I will take my problem Hamiltonian, evolve with it forward, and here I should go backwards. Sorry, this is a minus here. And then I just need to do a reflection around the state. So I have a state, I need to do some energetic mixing of this, then reflect around the state to say, well, try to go back, and then undo the evolution. It's like an echo operation. And that actually approximates the Riemannian gradient, which approximates the imaginary time evolution. And now we come to the algorithm where we will iterate it recursively. So as you said, this is now for now small. So I will get some output which is slightly less in energy, so I need to keep repeating it. So to do it systematically, we will have our input state 0, and there will be a unitary from all those unitaries here that gives me psi k after k steps. Just to say, I will need to rotate around this psi k, and the way I will do it is by using unitarity. So this psi k is a unitary that I can do, and then I can rotate around the input state, which is fixed, so I can decompose it by regular computation, and then I need to undo it here. Okay, so that's a unitary way of doing this unknown state through things where we know how to do. Okay, so we recursively assume I know how to do it the UK, and the 0 state is structured, so I know how to decompose that reflection. And then we have the recursion, right? So I will need to prepare psi k plus 1. I will do the reflection. This is the reflection. I will do the echo with the Hamiltonian, and I will prepare the state. Okay? And so by doing and undoing, I can be doing this commutator for an arbitrary state. And then I need to do the recursion. And as you said, this is the biggest problem of the method because we are linearizing. And so in every recursion step, we can only gain a finite amount of energy. Yeah. And that's the bullet that we need to bite. But that's something we did. So then we can decompose those two operations. As you see, this is again this unitary group law. Those two things we know how to decompose into gates. And those things are expressed again with h and 0. So we know how to do the whole thing, and that completes the cycle. And now I can tell you a little bit about the results. So we have actually rigorous theorems showing how much we should be reducing energy, but then we can also optimize how long is this step in the gradient direction, just by checking how the energy is decreasing. Once it starts going up, we terminate searching for S. So you see that we can start for a Heisenberg chain of 20 qubits. It's more than keys on the keyboard in one line. It's like a long one. And then you see 1 step, 2 steps, 3 steps, we are at the gap. 4 steps, 5 steps, we are inside of the gap. We are going to the ground state. So that's just one example of a spin chain where we can apply the method, and this is how it looks numerically. The other thing is that we can actually rigorously bound the convergence of those unitaries to the ground state. We get something which is reminiscent of general gradient descent algorithms. And just to say, if I start increasing the system size, so I start from 10 qubits, that's a small system size, and then eventually I double to 20, I will need more and more effort to achieve the fidelity. So given a fixed effort, I can achieve only a lower overlap, but that's normal, and that's the convergence question. And then I think I have a line. Okay. So just to put this into context, our method can start somewhere here and give you fidelity of about 90% within the runtime that is available on Quantinuum on trapped ions quantum computing. Okay. So that's roughly how the method performs. We are comparing to phase estimation because it's the canonical quantum algorithm for this. So I won't be discussing this too much.
So what is 0.5? 0.1?
Yes, so those are different variants of phase estimation. If you actually can solve the entire problem, you would parameterize it to this curve. But if you don't even know the norm of the Hamiltonian and you overshoot by maybe 1/2, it directly shifts and you need more precision. We assume here we know the ground state still, and the shift is quite dramatic. So we are showing that actually, if you don't know anything about the problem, then phase estimation will not be as strong as this actually, realistically. Okay, so that was the cycle that we completed just now. We started with a problem choice. I'm arguing material science is something that we can look at. And within the scope of material science, we need to look at optimization of energy to then study the properties on the state that we prepare. the design choice that we took was imaginary time evolution, and the unitary synthesis that we did was based on Riemannian gradients. And then once we took those kind of curvature approximation formulas, we had individual operations that we know how to decompose. Okay, just to say what we were doing is looking at different problems. So for example, diagonalization. Today I told you about this. We can also consider quantum signal processing. And we also studied Grover's search, which we can derive from imaginary time evolution in this paper. In all those cases, we found solutions for unitary synthesis in terms of exponentials of commutators. And now it shouldn't be a surprise to you, because in each of those cases, you can think of optimizing some cost function. When you optimize, you need to have some gradients, and gradients in quantum computing will always be exponentials of commutators. And then, so double bracket quantum algorithms are kind of designed for that.
For imaginary time evolution, that if you have exponentials of commutators, you showed that you can express that as, you know, some you can express that as some imaginary time evolution always, or no? Because there's this relationship, right? Like between psi of tau and the exponentials of commutators. So for all these different variants, did you use some kind of imaginary time evolution?
So in general, imaginary time evolution is approximated by this kind of update. And then I would need to perform it recursively. But if the Hamiltonian is special, like in Grover's algorithm, then actually I don't need this approximation. I can find some duration that implements everything.
But what about QSP?
For QSP, we proceed differently. So maybe I show the slides later for QSP. For QSP, we will be transforming the state by not applying the exponential of the input Hamiltonian, but the polynomial. And here we need to recursively decompose over factorization of the polynomial. So we decompose the polynomial into roots, and then those roots are kind of like gradient steps for us. And they are literally gradient steps, which we can show. And that's this paper, because we have those exponentials of commutators. So when we implement transformations through polynomials, we are also showing that we are effectively taking gradient steps. But this is out of scope today. I would need to start other slides. Okay, so that's the summary of the things we were doing. Just to say, there is a very powerful way of thinking about working on quantum algorithms through block encodings. You can have a look at this paper if you want to have a comparison. I'm not talking about this at all today. I was focusing more on a different type of how to think of unifying quantum algorithm design by thinking of Riemannian optimization. So instead of accessing H through the so-called block encoding, we were accessing H through the exponentials of the Hamiltonian, through the evolutions. So that was the unitary synthesis that we were looking at. And then through this, we actually found that we can perform optimization. So those Riemannian gradients were useful for that. Okay, so this is kind of like where it fits in more largely. And to finally summarize double bracket quantum algorithms, the distinct feature is that we are coherently implementing those Riemannian gradient steps. So there were no measurements throughout. Okay, many applications are kind of trying to work with the Schrödinger cut, ask a question, and then make a new cut and keep repeating. So you take a Schrödinger cut and then you collapse it. In those algorithms that we were looking at, so the line of work that we were looking at, we are never collapsing the Schrödinger cut. We are always working forward. And then the final one should be the magically low energy if everything went well. Okay, so that's the coherent aspect of those algorithms. I'm just summarizing here that we were looking at it. And the most important thing that we have ahead of us now is to actually ask people for help, to complain to us when it doesn't work. Because we are running out of ideas, we solve the things that we were able to solve. And if we get input about some weird behavior in some instances, we are hoping that we can improve on the theory and find new kind of quirky examples to get more ideas. So I would appreciate your input. And then in the scope of the AI revolution, just to say, one thing that we learned is, as a community, we learned that training quantum circuits from data, so machine learning, to do unitary synthesis just doesn't work well. Okay, that's the problem of parent plateaus. And as community, we understood that unlike in classical machine learning applications, quantum computation or unitary synthesis in quantum computation is not a good application of machine learning to the classical type. But what we found in our work is that those variational learning methods that don't work so well on their own are really super helpful as warm starts for our algorithms. And without those things, we wouldn't be able to achieve the energy lowering within the runtime that we wanted. Okay, so it's actually a very nice thing that we can use those methods now. Yeah, and that has been also some learning for me as well. And yeah, just feel free to stay in touch on LinkedIn, for example, as the curve code. Okay, I think let's finish this now.